is everybody can see this?
Yes,
Yeah.
perfect.
Thank you. Thank you very much for all the help, this technology related issues. Yeah, thank you very much. Well, the talk will go like this. My student who is currently at the University of Michigan physics program, so she will start with some discussion about a bit about the physics of the problem we are dealing, and then I will then talk about a theorem that I thought it would be interesting to mention in this talk. So I'll go ahead and just give it up to Ayla now, and she will start the talk.
Well, thank you. My name is Ayla Rodriguez. As he said, I'm calling in from the University of Michigan, and I'm here with Dr. Nog from Black Hills State University, and we're going to discuss the topological equivalence of the classical phase space and the maximal spectrum of the observables. Next slide, please. Thank you. So to do this, we're first going to talk about what the classical observables are, and then we'll discuss their algebraic properties. Realizing from the algebra that the observables form a ring, we'll use a theorem that relates rings to maximal ideals, the collection of which is called a maximal spectrum. With the maximal spectrum of the observables defined, Dr. Nog will take us through his proof that the classical phase space and the maximal spectrum of the observables are topologically equivalent. So to begin talking about observables, we must first begin by talking about real things in space. And all things in space are made up of particles, and particles have positions. And the position coordinates of these particles live in what's called the configuration space, which is a smooth n-dimensional manifold containing the generalized position coordinates at time t. And if we took the tangent of each of these position coordinates, we end up with the tangent space, a manifold of generalized position, and their tangents, generalized velocity, both again at time t. The union of tangent spaces is called a tangent bundle. Then there is the Legendre transformation, which is a function used to transform the coordinates of the tangent space into the coordinates of the phase space. The phase space is a dual vector space, or a cotangent bundle of the tangent space. It's composed of generalized position and generalized momentum coordinates at time t. And it's important for us to keep in mind that we're assuming the space is compact being closed and bounded. And we decide this based on physical nature. Since we're talking about things in space, we know it's not possible for a position coordinate to approach infinity. It's also not possible for a momentum coordinate to approach infinity, since momentum equals mass times velocity, and mass doesn't approach infinity, and velocity is limited by the speed of light. Since both coordinate, the boundaries are included, it is closed. So we decide that it is compact. Every combination of generalized position and momentum on the phase space is referred to as a state, which are described by Hamiltonian equations. So what the Legendre transformation really does is it derives the Hamiltonian formulation composed of generalized position, momentum, and time by preserving the position coordinates and dual vectors of the velocity coordinates to obtain momentum coordinates. The dynamics of states can then be described by Hamiltonian equations, where the Hamiltonian itself represents the total energy of the state from the preserved position and obtained momentum coordinate. To actually achieve a measurement of the state, the coordinates must be mapped to the field of real numbers, and it does so via real valued continuous functions called observables. The observables we define by curly O, which is the set of continuous functions that map coordinates from the phase space to the field of real numbers. We can learn a lot about observables by realizing at heart they are continuous functions. And we know if we add two continuous functions, we get another continuous function. So if we add two observables, we get an observable. We also know we can scale a continuous function to get another continuous function. So we can scale an observable to get an observable. And say we scale the observable by 0, then we know the 0 observable exists. And if the 0 observable exists, we can add two observables to get the 0 function, giving way to an additive inverse. We can also add the 0 function to an observable to obtain that observable, giving way to an additive identity. And we know then that the observables form an algebra. Continuing to consider continuous functions, if you multiply two continuous functions together, you get another continuous function. So the same holds with the observables, of course. And we see that the observables have the multiplicative property that is commutative. So Fg equals Gf. It's associative. So F times G times H equals F times G times H. We also see that through use of its multiplicative and additive properties, the observables are distributive. So F times G scaled by alpha plus H scaled by beta equals F times G scaled by alpha plus F times H scaled by beta. So additionally, supposing we had two observables, F and G, where G equals 1, we see that F times 1 equals F. So there also exists a multiplicative identity. And realizing then we have a commutative group with addition and multiplication goes under both, we now have an observable ring. Next.
Sorry. I went too far down, sorry. Okay.
Yeah, observable ring. So next there's something called Banach algebra, which is an associative algebra complete in the metric induced by the norm. So due to the Hausdorff topology of the phase space, where Hausdorffness is a space that is compact with separation property, and we know that points in real space are definitely separated. So this is a Hausdorff topology. So due to the Hausdorff topology of the phase space, we know the observables are bounded by extrema. So we define the norm to be the suprema of a given observable. The Hausdorffness of the space also necessitates closeness. So it's true then that every Cauchy sequence of the observables will converge to another observable, making this complete in the norm, and thus the observables are a commutative associative Banach algebra with identity. The last thing to consider about the observables is that it has the property of involution, where involution is an operation that maps a function to its complex conjugate and maintains the 5 subproperties outlined on this slide. A Banach algebra with involution is called a C-star algebra. So we know that the observables then make up commutative associative C-star algebra with identity. And so, of course, we know real numbers are complex numbers with their imaginary parts multiplied by 0. So for the rest of this presentation, we're only going to be referring to the real observables. So we're going to continue to use the curly O to represent them. Otherwise, if we were dealing with the complex, we would use a curly C. Considering then only real valued observables, we know they make up a ring, and rings have ideals. An ideal is a subset of a ring that's closed under addition and multiplication, and there's a theorem that says every ring, except for the 0 ring, has a maximal ideal. The maximal ideal is such that if for a set of ideals F, where M and N are in F, if M is a subset of N, then M equals N. If it were not maximal, then it would not equal N. A prime ideal then is a subset of a ring that contains ideals, but it contains only the ideals such that if F times G were in P, either F or G would be in P, but not both. So the identity is never included in prime ideals, because if F times the identity equals F, then F is in P, but we already assumed that the identity was in P, and we can't have both in P. So the identity is never a prime ideal. The maximal condition is that every ideal is contained in a maximal ideal, and a prime ideal is maximal then if there is no other prime ideal containing the given maximal ideal. So with all of this lined up, Dr. Naga is going to take it away by defining the maximal spectrum for the observables, and he's going to go through his proof of the topological equivalence of this spectrum and the phase space.
Thank you, Ayla. We'll just go over a slight definition of what is called a maximal spectrum. Now, there is the S there in that expression with M. That S basically is a point in the phase space. And that is this ideal M sub S such that all those observables such that F of S is equal to 0. This is a maximal ideal because of the reason stated here. It is the kernel of this map, and hence we'll be dealing with this object primarily, the M sub S. So the maximal spectrum is defined as here as all these M sub S. S is a point in the phase space such that M sub S is a maximal ideal. Now, this is our main understanding in this result, and the interest in this result comes from the idea that we were thinking that the phase space, which is a physical object, a Newtonian object, can it be expressed? Can that data somehow be obtained from the maximal spectrum, which is an algebraic object? And I think in pretty much modern thinking in terms of like this kind of research, it seems like the idea is to kind of somehow connect two objects from two different realms. And so that was kind of the idea that was motivating us. So in any case, so here we are, the main theorem is that this T star Q seen as a topological object is basically homeomorphic to the maximal spectrum of the ring observables. And so this proof follows an exercise in the famous book by Atiyah and McDonald, the Introduction to Commutative Algebra. So we'll just follow that. So in order to show that it is a homeomorphism, we show that G is surjective. And in order to show that if surjective, you have to show that you take a point in that maximal spectrum and show that there exists a point S in the phase space. Now the proof goes along this way, that we choose M, which is the maximal ideal of O. We don't know whether it is M sub S or not. And we're going to show that it is essentially M sub S. So now, first of all, this particular set, if it a non-empty set, then it is very interesting. So now the first thing that we do is that suppose V is empty, and then we go for a contradiction. And the way the contradiction follows is that, so if V is empty, that means for every S in that phase space, there exists F in that maximal ideal such that F of S is not equal to 0. Now, we know that these observables are continuous functions. So then we have this neighborhood over which also it does not vanish. Now, the good news about the T star Q was that it is compact. Now, I will again caution everybody clearly that usually the phase space is not compact. It has a lot of structure to it. It is actually a symplectic manifold, but it is not compact. This particular compact is a very special version of this. So I would point that out. So in physics, anybody interested in physics part of it, not necessarily you will get the phase space to be compact. Keep that in mind. Anyway, so here this plays a very little role that we get this union. A compact space can be written as a union of all these open sets. And now what we do is like we are constructing this observable, and we tell that F is equal to abs of this FS1, FS2, and so on, all these points. None of this vanishes. So it turns out that it is a unit. And in this case, it is 1 over F, literally. So now, but F is in M, which doesn't have a unit. So therefore, we have a contradiction. So now we have that V or B of M is non-empty. So now we choose any S in V. We have that set is empty. So now we have that S. And then you take any F in M, F of S equal to 0, implies F is in that maximal ideal corresponding to S. Hence, M is contained in MS, but wait a minute, M is a maximal ideal. So M is equal to MS, and thus we have the surjective part established. Then we go for injective. In this case, so here again that I think, yeah, that's good. So now here we have this compact Hausdorff nature of the space. So we have T star Q is normal. And here is this lemma that in general topology is quite interesting, where it says that two disjoint non-empty closed subsets of U and V are can be separated by a continuous function, where f of u is equal to 0 and f of v is equal to 1. Now, so we take 2 points, S and S prime, and then suppose, just for the sake of this discussion, let us assume that that gives us to MS, M sub S and M sub S prime, they are equal. So if they are equal, then, but S and S prime can be separated by a function, continuous function f, which means it is in the observable, such that f of s is equal to 0, but Ryson says that f of s prime would be 1, which is a contradiction. So that means ms cannot be equal to ms prime, and therefore we have the injectivity of G. Now, somehow, I actually written this part, but I think hopefully this is clear from my description. Somehow I didn't reload my newer version of this. Anyway, finally, we will show that G is an open map, and we take these two sets, UF and VF. UF is all those points S in T star Q such that the continuous function is not equal to 0. So that is open. And VF is all those M spectrum of O, which is F not in M. Now, it is a good exercise to kind of form the basis of a topology. So we are going to show that G of UF is equal to, so we're basically operating on the basis sets. So here, then we go for the proof. I'll just, basically it is standard. We just show that G of UF is a subset of VF, which is pretty straightforward from this thing. Then the other part is that when I am going to show VF is a subset of G of UF, I take any M is in the spectrum of Maxwell spectrum of O, such that F is not in M. Then G is surjective. So there's a point in S, which is in the space such that F of S is not equal to 0, implies that G of S is equal to MS. But what is MS? MS is all those F such that F of S is not equal to 0. So then again, M is a subset of MS, but M is equal to MS, which is in G of UF. So then VF is a subset. So thus we got that G of UF is equal to VF, and hence the phase space is homeomorphic to the maximal spectrum of the observable. So that gives us a algebraic characterization of the physical object called the phase space. The underlying assumption, of course, is that the phase space is compact, which is a technical assumption that was very important for our discussion. Few references here, just for the sake of it, Marsden and Abraham for understanding some of these concepts on Hamiltonian and other physics aspect of it. And then we did quite a bit on commutative algebra by Atiyah MacDonald. Gelfand Neumark proved these ideas, similar ideas, some time ago in their famous 1943 paper, and there's a book associated with it. And then the C-star algebra formalism of quantum mechanics was also a good insight about the algebraic aspect of it, of all this. And a future work would include some sort of understanding of the symplectic structure that is there on the phase space, realized as a observable. That's a work in progress right now and thinking. And then this is an application. It's a kind of interesting application book called Introduction to Algebraic Geometry. Was useful in this idea. Well, that's about it. So love to have any questions, and hopefully didn't go too much above the time. So
questions, anybody? One nice thing about virtual is we don't need the full 5 minutes to go running in and out of rooms.
Yes, definitely. That is very helpful. And also, hopefully this, I mean, there are things here that easier to, especially now today, because there is a blizzard going on outside right now in where I am sitting. So I'm attending the conference in the middle of a blizzard. So that is actually also tremendously helpful.
Well, it's always nice to see Eurozon's lemma in action. I just have one sort of silly, naive question. I was trying to think what the zero element would mean in the observables.
The zero observable.
Yeah.
Any insight, Ayla, about the physics?
That's a really fun thought, isn't it, actually, right?
Physics
'Cause
observable, yeah. What is
something
that?
with no
Could be,
position and no momentum, that's something
you
that's
got
not
zero,
real.
yeah. You got zero output, basically, from the signal, I guess. I mean, which means like there is no signal, I guess.
What a fun
I don't know
thought.
what that would mean. I would think that it would be no signal, because, or maybe you have a signal which is just everything is vanishing. I mean, just
A black hole.
the useless signal, yeah, the useless signal, yeah. Or could be
Other
there is
questions?